All right, welcome back everyone. We are on our final session of the day. This is going to be a response to a reverse pitch. We are going to have 3 different presenters. We'll have Inez from Stanford, Lalita from MSU, and Gabriel from UNCC. We are going to start off with Inez. So Inez, over to you. Good luck.
Thank you, Anna. So I'm really excited today to present an initiative and project that we just started at Stanford University. This is called Mesmerize, the Macro Energy System Model with Equity, Realism, and Insight into Zero Emission System. We're fortunate to have assembled a really interesting team of faculty. So myself, Ram Rajagopal, Jack Shalendar, Adam Brandt, and Sally Benson, and John Wyant. And so the vision is really to accelerate the deployment of effective and equitable energy solutions for climate mitigation by providing reliable information about the most effective and realistically implementable pathways, as well as identifying the costs, benefits, and societal and environmental impacts of deep decarbonization transitions. So really the key research question that we want to address in the next couple of years is what are the realistic and implementable pathways that are sustainable and deeply decarbonized, and that include explicitly in the modeling real policies and their interactions and the way people make decisions and behave, as well as to account for environmental justice. So this really falls under a response to the reverse pitch on decarbonization and customer engagement, such as the one that was shown in the previous session with the presentation from LADWP's decarbonization. So our goals are first and foremost to develop the people and policy-centered computational hub at Stanford, both on with a focus on the overall energy system and a climate science and mitigation lenses. We want to inform policy. So this will be at the forefront of deep decarbonization and environmental justice research with explicit descriptions of upcoming policies. We also aim to develop the modeling capabilities at Stanford by supporting an interdisciplinary simulation and optimization modeling platform that will allow us to perform test beds about the most effective technological, financial, and equitable solutions as to describe real decisions. Yet another goal is to provide resources to others. So the modeling platform and outputs will be all available for use and display to the public and to other researchers. And hopefully there will be a benefit for both Stanford researchers as well as the general public. And Anna, I see that my slides disappeared on my screen. And here they are. Okay, great. And finally, we aim to induce collaboration both within Stanford across several PIs, but also across the broader community at Stanford and outside of Stanford. So a little bit on the motivation on why do we need this sort of modeling platform and data sharing process. In the first instance, moving towards a decarbonized, sustainable, and just energy system means designing technologies, policies, and interventions that will be able to gear us in that direction. So the climate problem is, in a first order, an energy problem. And most of the work today that has worked on deep decarbonization for energy systems often takes on a center planner optimization perspective. And we know this is not how the real world behaves in terms of decisions in different actors. In addition to this expansion and new look from a central planner to several agents, there is this connection between climate change and air pollution. And those two things are extremely different. So emissions of greenhouse gases will last for a long time in the atmosphere and have implications for future generations, whereas the use of fossil fuels also contributes to the emissions of SO2, NOx, and PM, which lead to premature mortality with effects that occur much more rapidly and close to the source of the emissions, whereas the emissions of GHGs will be global in their dispersion. Um, a fourth lens is that energy technologies, both in the current system and potentially future technologies that can be deployed, such as solar PV and electrified vehicles, may have associated externalities not only on climate change impacts and air pollution, but other sources of externalities relative to access to those green technologies, the way the green subsidies are distributed, and access to green jobs. And so we want this modeling platform to explicitly have a detailed, geographically dependent environmental justice output considerations. And finally, most of the work on the deep decarbonization has taken an optimization framework looking at the least cost strategies, but this really ignores the patchwork of climate, air pollution, and economic energy policies that a nation or a region may be putting in place altogether. So it's an explicit modeling of the policy design and how policies are interacting are key to understand the outcomes from changes in energy systems. And many of these aspects are going to be very location and population specific, which in turn requires granular data and data analysis techniques to help with this modeling. And finally, a lot of these decisions and data analysis problems have tremendous uncertainty, so an explicit goal for this work will be to have a detailed treatment of uncertainty too. So this vision, which we've called Mesmerize, includes several things. First and foremost, energy and climate change mitigation model in-house that will apply first to California and then hope to expand for the US and for other regions. It will include a computational AI tool that is going to be available to researchers, students, and the broad community. We also plan on harmonizing data sets that we have identified several researchers may need and that simply don't have a unique repository, and also, when necessary, public form of data products. So a little bit about the modules that will constitute Mesmerize. First, we'll have a first module describing how people's energy demand is driven for different types of activities at home with the characterization of the building stock, at work, and getting to places. At a later stage, we hope to also incorporate behavior towards purchases of goods and services, but not just yet. A second model will characterize the energy supply and storage. So this will have a detailed characterization of the grid and the power systems with the location and capacity of power plants across the country and their emissions, as well as other fuels and streams that may be necessary to meet energy services. A third model will be associated with the production of goods, and this one will be an emphasis for a later stage of development. And finally, a fourth module that also includes the policies and programs that are planned and into place. Now, these modules are going to interact with a module that is tracking the costs, the benefits, and the externalities associated with different types of technologies. And so, at the very least, the externalities that we'll consider will include the climate change damages associated with different pathways, the health damages associated with air pollution, and for the transportation sector, an important externality is whether some of these strategies will change congestion, since there is an important economic penalty associated with those. And finally, the sixth module will account for the environmental justice aspect, so defining the set of metrics that allow us to understand how the health and climate change impacts, as well as technology access, will differ by income, race, and ethnicity, and as well as the distribution of costs and bills for participants in the system. So overall, outputs will be the economic costs and benefits of different agents and the distributional and environmental justice outcomes associated with different scenarios. Each of those pieces will be modular so that researchers can really invest in developing one of the modules and then plug it to the other models for interaction. And again, we'll start with the detailed characterization of California, both for the underlying data and proposed policies as a testbed for this first year of model development. Our group has been working in pieces of information that are going to be very beneficial to this overall model structure. And so I'll cover a few examples. The first one is our tool that tracks real-time consumption-based CO2 emissions and air pollution emissions estimates. This has been published in PNAS. And as you can see, hopefully the animation on the right, those small is visible on the changes in emissions intensity that occur from hour to hour in different regions for different balancing areas. So first usable product is really how much are we emitting? But this doesn't really get at the damages induced by emissions of pollutants. So for greenhouse gases, this calculation is simple. We can assume that emissions are proportional to a damage and assume a social cost of carbon. But for air pollution, where you emit those pollutants and where ultimately they end up increasing the concentration of PM, maybe two very different stories. And the air pollution will also depend on how many people are exposed to high concentrations of pollutants. So I'll get back to that issue of damages in a little bit. But first I want to cover second data product from previous work. We looked at the distribution of adoption of solar PV across the United States. And so what this shows is really how the distribution of solar PV compares to the distribution of income across the United States. And we're showing that for 2 years for 2014 and 2006. So if we see a distribution of the curve of the adoption leaning more towards the right of the population curve, this means that really high income households are the ones that predominantly are being the adopters of solar PV. So not entirely surprising, but the situation is improving since 2006, meaning when we think about subsidies for green technologies, in the case of solar PV, this was a high income household benefit given that those were the key adopters. And so we aim to see whether the same set of issues arise when we think about adoption of electrified vehicles or the adoption of storage technologies for homes or even microgrids. A third data product is tracking the marginal emissions of different types of power plants. And I'll motivate this with an example. As you charge your electric vehicle or turn on your lights, you have an additional load that increases in your house. And the electricity that you're using for that load won't correspond to the average fossil plant or the average electricity mix in the plant. It will be attributed to a specific set of power plants that need to ramp up and generate power to meet that last bit of demand. So what our group has done is to use both regression-based techniques with historical data as well as simulation techniques with detailed characterizations of the electricity fleet to identify for different regions or balancing areas what are the sets of power plants and their characteristics that are meeting the last bit of power to meet that demand. And not only that, but we have coupled that with air quality models to understand what are the air quality damages and the greenhouse gas damages associated with meeting that load, or you can think about it the other way around, how much of that pollution and damages is being decreased as we deploy things like energy efficiency or retire a few set of dirty power plants. And we've made all this data already available as a repository where researchers can download damage factors and emissions factors by balancing area and by time of day to use in their own simulations for different energy interventions. Another issue that we'll tackle is the issue of reducing temporal complexity. This is a challenge of scales. We have power systems that involve investments over decades. We'll have coal or nuclear power plants sitting around for between 40 and 60 years or more. And we need to couple that with models that need to meet demand across generation in the power plant fleets at the sub-second level for those decades. So how can we define and develop models that optimize the system level behavior, meaning the types of investments in new generation capacity, retirements of old power plants, and decisions on transmission expansion when the results are also sensitive at the sort of second or sub-second level decision makings. So my colleague Adam Brandt and his students are working on new techniques to understand how to reduce this temporal complexity between operations of the grid and long-term investment decisions that will be incorporated as a module in Mesmerize. So with that, I'll end that we're very excited about finding both applications and areas where we can use this overall philosophy of modeling on macro energy systems, taking into account these different aspects. And we really look forward hearing more from colleagues and from the industry and from EPRI on additional issues that we can tackle over the course of the next few years. And with that, thank you. And Anna, back to you.
Thank you so much, Inez. That was great. Okay, we are going to go next to Lalita from MSU. Before I do that, I just want to remind everyone to please use the chat and Q&A feature on your screen. We will probably have time at the very end to get to a few of those questions, so don't forget to use that. All right, Lalita, over to you. Thank you.
Let me go to my first slide. Okay, my name is Lalita Udpa. I'm with the Electrical Engineering Department at Michigan State University, and I will be making this presentation along with two more of my collaborators and colleagues, Professor Beng and Professor Zhang. So before I go to the next slide, I did not quite see the term NDE used in this workshop. So for those of you who are not familiar with that, I'd like to define NDE is non-destructive evaluation. And basically what we are looking for is structural integrity of different assets when we do an NDE inspection of an asset in the nuclear power plant. So let me talk a little bit about our MSU, NDE, and AI group. We are about 6 faculty members in this group with 3 postdocs and about 25 PhD students. Working on different funded projects that I've just listed here, just to show the capabilities of the group. So we work on aerospace, automotive, transportation, basically, natural gas distribution and transmission pipelines, biomedical applications, and for the Navy, we're looking at wireless sensor network for structural health monitoring. So these are funded by different agencies, as you see there. And I would like to spend some time in this talk to describe 2 of the EPRI funded projects. These are funded by the SGMP program in EPRI with Jim Benson as our program manager. And the reason I want to talk about this is that the research results that we have in these 2 projects, I feel, can be leveraged to address many of the issues that have been raised in the past 2 days, particularly in the asset management and digital twin sessions. So in particular, I'll talk about the automated data analysis, which consists of a lot of machine learning, adaptive learning, continual learning algorithms. And we've also looked at simulation models for steam generator tube inspection, which serves as a digital twin that can augment a lot of the performance of the automated data analysis system. So the next slide is basically tells gives an NDE and AI framework which intermingles all these tasks involved in NDE and AI to achieve basically the optimization of asset management. So we have an NDE, AI-enabled NDE sensing, processing, and in NDE, there are two major problems. One is the forward problem, where given some kind of degradation in the asset, you simulate the sensor physics and predict sensor measurement. So this is very useful. It's a digital twin for, or what I think one of the speakers called as the operational twin for this particular asset. It also can give you uncertainty quantification. We can look at the effect of various parameters, environmental parameters that will affect the sensor measurement. So, so one of the things in AI is we do need a lot of data. So we can use a lot of experimental data as well as simulation data to create an augmented database. The other interesting problem in NDE is the inverse problem. Here we are looking at, given a sensor measurement, can we predict or characterize the degradation in the asset that you're trying to inspect? So in the inverse problem involves a number of different tasks, machine learning tasks for classification, which are mostly neural network based. We can do profiling, we can do adaptive learning, and federated learning with Professor Zhang. We'll talk about more in more detail. So once we have the output of the inverse problems, we can actually use that in conjunction with the digital twin to calculate the remaining useful life and use it for condition-based or predictive maintenance type of questions. So in general, the overall objective is to optimize the asset management system. So moving on to the first of the EPRI project. The first project that I would like to talk about is the auto analysis project, which is basically consists of machine learning and AI algorithms. This was for particularly refers to the steam generator tubes. So this was in this SGMP program. One of the things we all realize in the last 2 days is whenever you want to develop a machine learning AI for SIG data analytics, you need data. So EPRI did have a program where they collected steam generator tube inspection data from multiple plants with multiple degradation mechanisms and multiple probes. And so we had access to this data. I think it's called the AAPDD data, which is the Auto Analysis Performance Demonstration Database, which is also used for training human analysts. So we use this database along with expert knowledge to develop this machine learning expert system module for analysis of steam generator inspection data. And this basic module is a standalone software, and it has been validated with this database, and it was also validated. It was field tested. It was taken to several plants during outage, and along with human analysts, data was also provided to the this module. And I don't have the results, but the performance was identical to human analyst performance, and with the additional advantage that whereas it took about 17 hours, I think, for the human analyst, the auto analysis package, software package, was able to do it in about 40 minutes, which is not surprising, really. So we had this basic model, which was released to various utilities. In the next phase of this project, we looked at real-time statistical analysis. You know, one of the things that I think Steve Oren brought up in this keynote talk today is the AI system is only as good as the data you provide to develop the model. So what happens at the time of testing, you encounter things that was not used for during training. So in the next project, we developed statistical analysis algorithms that takes into account the feature quality, the kind of inadequacy or of data during training, the data quality, is it a noisy data or clean data? And also, if we have historical inspection results available, these are all augmented to improve the performance. And also, when we had multi-sensor data, we were able to do some data fusion to get better performance. So the basic idea of the statistical analysis is to evaluate the performance of the AI system. So we were able to quantify the reliability of this AI system by computing a confidence metric using Bayesian probability, posterior probability type model. So what do we do with this confidence metric? If the confidence metric is very low, it basically says there is less confidence in the AI system performance. So we can either have an operator to intervene, or we can also use invoke the digital twin to take the data and do some kind of reverse engineering to determine accurately the degradation mechanism that generated the signal. So this is in this, and then the result of this reverse engineering can then be used to retrain the AI system. So we were able to propose an adaptive learning or a continual learning framework for the AI module. So the end result, of course, is to be able to have increased reliability of the AI system uh, to give a more informed decision that can be taken. And it also be used, the performance of the AI or the output of the AI system can be used in conjunction with this digital twin to also estimate the remaining useful life and provide some kind of risk-informed or predictive maintenance approach to the overall inspection. Now, in the second box over there, we also developed a standalone neural network-based algorithm for profiling of the stress corrosion cracking. And in that, you can see that these were actual stress corrosion crack, which are metallographically determined. And the magenta and the blue curves that you see is the profiles that were generated by using simple algorithms that are now currently used in industry. And the deeper the profiles were the actual metallographic profile, which matched very well with the neural network-based software that we developed for profiling of the defect. So, and the third box there is an extension of the basic algorithm using deep learning, and Professor Deng will talk a little bit more about this particular thing. Okay, so in the next slide, I want to Okay, yes. So I talk about the second project that were conducted during using EPRI sponsorship. And this is for developing a software tool that simulates the tube inspection using eddy current probes. These are commercial probes. Basically, the features of this particular software is it can simulate different types of tube geometry, the free span, the drill support, expansion transition geometries. It currently supports many commercial probes, bobbin probes, and the rotating pancake, and the plus point, and the shielded pancake, as well as the array probe. And it also, with the user interfaces, user can also input different defect geometries, different location, different shapes, and orientation, and so on. So this is another software. This is been just to show you a little bit about the validation or the accuracy of the software. The software uses finite element analysis of electromagnetic problems, and what we see here is a comparison of the simulated signals with the experimental data. At the top row is the experimental data. This is a very simple bobbin probe. The next slide shows a comparison of OD axial notch using plus point probe. On the left, you see is a calibration defect. So you see the calibration signals from all defects using the experimental system. And on the right, you see the simulated signals from one of the calibration defect. And the third slide validation result I want to show is a real crack profile. This is again a database that's there in EPRI. We were able to very easily provide an arbitrary crack shape and use that. And this, and there's again, once again, we can see the simulated and experimental defect comparison. So with that, I'm going to move to the next speaker.
Okay, so the second part of this talk, we're going to talk about how we can, design and develop the AI and NDE framework for asset management and maintenance. Because of time, I won't touch everything in detail, but I just mentioned that the ongoing work at Michigan State include the novel sensor development, both wired and wireless. And we also do sensor auto calibration and intelligent control. I'm going to talk about that through an ONAR project. Then we have to do network optimization, sensor simulation, and everything will actually be useful for digital twins development, and eventually going to lead to the proactive prognosis and prognosis and reliability based predictive maintenance with uncertainty quantification. So this is just a framework showing you that this is for a motor controlled valve for nuclear power plant application where we apply the wireless sensor, get the NDE measurement, send the monitoring diagnostic data into the decision support system where we can lead to a optimized decision making. Of course, the expert inputs and the historical data are very important as well. So for this slide, I can talk about the Navy project where we develop a real-time fiber optic sensing and actuation. Here, actuation means that we're going to use AI to do the intelligent control of those sensors. You think about we are now not listening to all the sensor data at the same time, but using AI to understand where and when to gather data and control those fiber optic distributed sensor network. This just showing the schematic of the sensor network with the size of the sensor, and this picture show where the AI going to play this critical role in control the sensors as well as the data analytics to lead to the final decision making. And my last slide, I'll talk about another ongoing work, with the collaboration between NC State, Idaho National Laboratory, and the industry direct solutions, where we are proposing a solution to deploy wireless sensors for nuclear power plant infrastructure. This is a containment structure where we strategically place the sensors, get the data, and those red is actually the core, while the green is where we place the sensor and the locations at a parameter of this structure, while using AI to control multiple sensors at the same time, do the data analysis and feedback to our system to achieve the better data analysis outcome. So this slide actually, I'm going to bridge this with the work I'm doing with Professor John. He's going to talk about how to use AI to solve 3 key aspects in our AI plus NDE framework. So I'm going to pass this to Professor John now.
So in the past few years, we have witnessed the breakthroughs of AI in many different fields. At MSU, we have made some fundamental contributions to this breakthrough. One of the key aspects of this contribution is to enhance the efficiency of AI-based solution. Many problems, especially for diagnostic and prognostic problems in electrical power systems, requires real-time inferences. However, we do know that the power of AI comes at a cost of efficiency. So at MSU, we have contributed fundamentally to enhance the efficiency of AI so that the AI-based solution can deliver real-time inferences results. The second contribution we make to make AI better is that we do know that data are great assets for all the possible AI solutions. And the solution we developed for electrical power systems is no exception. However, in many cases, data are private right? Enterprises have their own private data, and there's a barrier to sharing those data across enterprises. At MSU, we have developed this further learning framework where we can enable multiple enterprises to collaboratively build AI models for many different applications without even sharing their private data. This is actually very helpful, especially for data are private and are truly private for many different enterprises. The last contribution I want to talk about today is the automated machine learning. We do know that the AI-based solution requires a lot of expertise to develop. In many giant companies like Google and Facebook, they have a team of professional AI experts to help them develop AI models. However, for many other companies or enterprises that are in other different fields, developing such AI-based solution is costly. So we have contributed to this automated machine learning framework that can automatically design high-fidelity AI-based solutions without human experts.
Okay. Oh. So the last slide basically, talks about our capabilities, and basically we look at asset management and digital twin. We look at 3 different challenges where we have worked on and things that we have the capability to work on. Okay, so that is, I think, the last slide. And with that, Hannah, over to you again.
Awesome. Thank you so much, guys. That was a great job. Okay, we are going to move on to our last speaker of the day. It's going to be Gabriel from UNCC. Just a quick reminder to post your questions in the chat. All right, Gabriel, over to you. Thank you very much.
Thank you, Hannah. Hi, everyone. My name is Gabriel Tejano, and I'm an associate professor of computer science at UNC Charlotte and the director of Uncertainty Quantification Research Lab. The title of my talk is Discrimination of Operating Regimes Using Physics-Informed Neural Networks in Motorized Systems. What I'm going to present is mainly related to resilience and outage optimization, specifically to equipment condition monitoring and impact of transmission outages. To motivate this talk, I would like to give you a brief overview of my background. Prior to my academic appointments, I have worked as a software engineer and a quantitative researcher in financial services. And during my academic tenure, I have collaborated with researchers in various domains such as chemical engineering, aerospace, and microbiology. In this talk, I would like to share with you what I have learned in these multidisciplinary collaborations and by modeling physical systems. I will also try to answer the question how I am currently using this knowledge to develop data-driven models based on deep neural networks. And I will give you some examples of the problems that we are working on. To start, I would like to make a contrast between models developed for physics and engineering problems and models used in data science. We all know that nowadays, models are more prevalent than ever in guiding our decision-making. From civil engineering to aerospace, we have been using modeling and simulations to design bridges and airplanes. From marketing to insurance, we are using models to optimize marketing campaigns and insurance portfolios. Try to answer the following question. Predictions of which type of model would you trust more and why? Would it be the physics-based model used to design a bridge, or the data-driven model used to optimize a marketing campaign? The answer to this question became more apparent to me when I worked on a problem relevant to the Department of Energy while I was at UT Austin. It was there where I learned that the US needs to certify its nuclear stockpile without doing any nuclear testing. This is because of the Comprehensive Nuclear Test Ban Treaty. How is it possible to certify something without having experimental data and relying on modeling and simulation? While this is an extreme example, there are many problems out there where experimental data at the full system level is either non-existent or very expensive to obtain. While we'll hardly encounter these types of problems in data science, it is instructive to understand what makes these physics-based models more trustable than data-driven models. In data science, to build a model, we start with data, lots of data. It is unthinkable to do the same for a model used to design a bridge. How many bridges do we have to build, experiment with, and take down to build a model of a reliable bridge? In physics and engineering, to build a model, we start from first principles, such as conservation laws. A conservation law states that a particular measurable property of an isolated physical system does not change as the system evolves over time. These conservation laws provide the scaffold for the differential models of these physical systems. There are many conservation laws. In the following few slides, I will show you how we are using the conservation of energy. Consider first a simple problem, namely predicting the position of an ideal pendulum using its previous location. Since we are dealing with an ideal pendulum, we know there is no friction, and thus the pendulum will never stop. In other words, the energy of the pendulum is conserved over time. As a data scientist, I would jump to record the position of the pendulum over a large number of time steps, create a data set of lag 1, and build a neural network using this data. A mechanical engineer, on the other hand, will exploit the fact that energy is conserved and derive a differential model using this property. In other words, she will use the conservation law to constrain the predictions of the model. The reality is that as a data scientist, I might wrap my head around that the system conserves energy. However, I will not have enough domain knowledge to fully characterize the system and express the energy in terms of position and other quantities as a mechanical engineer does. The good news is that there are a number of developments in the AI community, such as the development of the Hamiltonian neural networks, that leverage the power of neural networks to find a suitable energy function using experimental data to constrain model predictions. Now, to be able to apply the Hamiltonian neural network as a data scientist, the only domain knowledge that I need to know about the system is that it conserves energy. You see here the striking difference between the predictions of a plain vanilla neural network, shown in red, and the Hamiltonian neural network for this ideal pendulum, which is shown in blue. The errors in the predictions of the plain vanilla neural network accumulate really fast, and we see that this type of neural network does not conserve energy. Next, I would like to show you how we are using these Hamiltonian neural networks to develop a model for anomaly detection in motorized systems. We have been working with data collected from a motor that drives a shaft. The goal is to detect anomalies during its operations. This is important for a large number of applications that use this type of system, such as condition monitoring for helicopters, windmills, and CNC machines, just to name a few. I believe that the same principle can be applied to other assets that are of interest to you, such as transformers. In this experiment, we have introduced various defects where the shaft is supported by the bearings and added various loads on the middle plate. The data that we are collecting consists of vibrations, sound, and speed measurements. While this system does not conserve energy, here we have friction, we are adding energy through the use of the motor, and we believe that the assumption of energy conservation still holds, but for short period of times when the speed of the motor is constant. As a result, we have used the data collected to train a Hamiltonian neural network. However, the issue was that we had no idea what position even means in this case. How should we go about to generate a representation for this particular system that will be used to construct the energy function. To solve this problem, we have used autoencoders to generate a low-dimensional representation for our energy function. Nevertheless, while we use this low-dimensional representation in training the model, our intent was not to predict its evolution over time. Remember, the goal was not to predict the position, but rather to identify whether the operation of the system was abnormal. Our assumption is that we can use the learned energy function to discriminate between normal and abnormal behavior. Here we see the energy function corresponding to the normal behavior and 5 other energy functions corresponding to different anomalies. While the energy is conserved in all cases, the behavior of the system is different, and it is reflected in the shape of the learned energy function. This allows us to discriminate between normal and abnormal behavior. All of these are possible by using very accessible domain knowledge about what is conserved or invariant in the system. We also have quantitative performance measures to show that this type of physics-constrained neural network provides good discrimination between operating regimes. Now, I imagine you saying, Gabriel, this is great, but how can this work for non-physical systems? What is conserved in those systems? While I don't have a definite answer, I believe that one thing that is conserved is the cause-effect relationships between variables. Machine learning models are correlation-based models, and they can only answer what if I see type of questions, while causal models can answer what if I do questions. With causal models, what we try to do is to understand the impact of an action in the real world rather than looking at passive predictions. This is relevant for developing causal cost models when trying to identify the impact of planned outages. Most of the models we have in data science are correlation-based models because they use observational data. Causal relationships are traditionally discovered using randomized experiments such as clinical trials. However, there is a real need to develop causal models from observational data when randomized experiments are not possible or very expensive to conduct. There is a large literature body of discovering cause-effect relationships from observational data. New research, such as no tears, tries to make causal discovery scalable using modern tools. We have developed an interactive and iterative causal modeling framework that leverages automatic causal discovery from observational data and expert domain knowledge to be able to reason about the causal effect of an intervention. The problems that we have been working on are more business-related, such as understanding the causal effect on sales or insurance premium. What we have found is that using expert knowledge about few cause-effect relationships and constraining causal discovery algorithms, we are able to correct additional causal mistakes. This is important because we can obtain better estimates of causal effects for various interventions. In conclusion, the way I think about building models is by first stating what is the conserved property, for example, energy or causality. This will be used to constrain our model. Furthermore, I'm thinking about the additional domain knowledge that I can use to further reinforce this conserved property. For example, the timescale of data or the few known cause-effect relationships. Finally, during model validation, I search for evidence that the model does indeed conserve the desired property. The first physics-informed example is applicable to EPRI challenges such as equipment condition monitoring and predictive maintenance. And the causality approach is applicable to building cost models that incorporate causal relations to calculate the effect of planned outages. I would like to acknowledge my current students that have been working on these problems, Jeremy, Jawad, Reza, Anir, Gurav. I also like to give a special shout out to Jeremy. While the other students are graduate students, masters, and PhDs, Jeremy is a high school student and he did a fantastic job on the Hamiltonian neural network. I also want to acknowledge my current engineering collaborators, Rav and Andreas from University of South Carolina. We are looking for collaborations and new case studies where we can apply these ideas. Thank you. Back to you, Hannah.
Great. Thank you so much, Gabriel. All right. It looks like we do have time for a few questions. I'm going to start with Inez. Inez, you had a very interesting and impactful topic. How can others in the audience get involved and help to make an impact in this area?
Thank you so much for that question, Anna. I would say that reach out. So happy to provide the contacts and email. We'll start getting organized on mapping out the data sets and data products that are already out there that could be usable to a broader research group. So identifying whether you have similar efforts that are going on would be most useful. We're also recruiting currently postdocs and PhD students to help with this effort. So for folks in the audience that are at that stage, please send your CV. And otherwise, just reaching out and having a conversation on the plans that we have. This would entail 2 planned workshops for the next academic year. And so happy to hear your thoughts and interest in participating in those.
Thank you so much, Inez. All right, Lalita, what AI solutions or which successfully deployed solutions have you brought from other industries using NDE to the electric industry?
Well, thanks for the question. What we have done, I don't know whether this was used in other industries. Maybe I'll ask my collaborators to add on their comments. But I think the tools that we have used in the beginning are just basic generic machine learning, and it's like Gabriel pointed out, it's mostly coordination, pattern matching, taking a bunch of data and having the class label. We looked at pattern recognition, advanced pattern recognition algorithms, later on we looked at the statistical algorithms to self-evaluate the performance of the AI system. So, do you guys have anything to add to that? I think they're working on other industries.
Yeah. So for the projects that I'm leading, that we mainly working on Department of Energy and Department of Transportation, where we deploy AI to understand the infrastructure safety and the reliability. For that aspect, the most important, I think I echo a lot of people mentioned in previous talks, that data is definitely critical. So how we can deal with limited data to us. The other thing is how we can use AI to understand the existing data, including historic data. Some of them not in the form of like NDE measurement. It can be probably text and other heterogeneous form. So how to use AI to understand those data inputs, that's important. The other aspect of this is how to do a better information fusion. I heard some speakers mention that concept. So use AI to do a better information fusion and understanding. I think that's another level of understanding of AI, in particular our NDE. Some people mentioned the term of monitoring and diagnostic. I think that's the same or very similar idea. I don't know if me won't add anything about this from his aspect.
I think the data federation of data or something.
Yeah, so I echo both of my colleagues here. The central asset, as I mentioned before, to AI is the data themselves, right? So at MSU, we have developed a lot of novel techniques to either create synthetic data to basically use the synthetic data to help train a better and more powerful AI model, or using the federal learning techniques I talked about, basically without intruding the privacy of different parties, we can collectively train a better and more powerful AI models by joint forcing the data from the private parties. So the data again, I can't emphasize more how important the data plays in all the AI-based solutions. I believe electric power system is no exception. Thank you.
Great, thanks to all three of you for that response. Gabriel, we have a question for you. What other challenges do you think you would be able to address using these models?
So while we haven't specifically worked on energy-related problems, so that these are applicable to those. So the first one, obviously, the physics-informed neural network, that can definitely be applied to anything that has a rotating shaft, right? So if we are able to look on the generation side of electricity, we look at windmills, turbines, anywhere we can actually be able to directly apply this kind of technology. However, I found that the most challenging aspect in implementing machine learning models is actually getting them to work in a production environment. So we do a great job training them. However, while we are actually moving in production, or we try to use them in situations for which we haven't seen the type of data that we see in training, they fail miserably. And I see this in my collaborations in where we look at design of materials. We are looking at developing new catalysts. I'm working with Andreas Hayden from University of South Carolina, so we try to develop new catalysts and try to accelerate that and create virtual screeners for new catalysts. And to do this, it's really challenging. I mean, we implement these models, but at some point they become problem dependent, and moving the AI from one problem to another problem, having this transfer of knowledge, this domain transfer becomes very challenging. And I see this also working with companies that also they look in material innovations, and also on the side of just more business related problems. So I think that this concept of invariance in machine learning models is very important, crosses a number of applications, and we shouldn't stop there. These models are, we don't just apply them in isolation without any additional knowledge. Everywhere we use this, we also have domain experts, and they already know a lot about that problem. And if we can actually try to elicit some of that expertise and incorporate into the models, they will be so much better.
Great, thank you, Gabriel. Okay, we're going to have one last question for Inez. So you are one of the leads for climate change AI. Can you tell us a little more about climate change AI, and how does your project relate to that effort?
Oh, yes, they are fairly, they are distinct. Climate change AI is this super interesting initiative that was initiated by postdocs and PhD students that were working at the intersection of those topics, and that actually wrote quite a seminal paper on the issue. And I was fortunate enough, along with several other faculty members and researchers, to be brought on just on an advisory role to the group on the type of research that they are performing. I would strongly suggest following up the climate change AI websites. They have been pretty active in terms of their roles in participating and organizing also sessions at key conferences. I would say that the effort on the modeling approach that we're doing is something completely independent from the climate change AI initiative that is going on, but would definitely welcome interactions and recruiting potential folks that are interacting with the climate change AI to this major effort. This initiative, well, there is yet the other initiative at Stanford on climate change AI overall large umbrella that has sponsored two different projects as an initiation, and we're really excited to see that area grow in the next few years.
Great, thank you guys so much. All right, that is a wrap on day 3. We will be back here tomorrow at 9 a.m. Eastern time for our last day. We will go from 9 a.m. Eastern to 1 p.m. Eastern. We do have some breakout sessions, so make sure you join us back today. Special thanks to all of our speakers and presenters. You guys all did a really great job today. All right, everyone have a great evening, and we will see you back here tomorrow at 9 a.m. Eastern. Thank you very much.